Hello everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 2.3 and this is the beginning of our more detailed treatment of the memory model and locality. And we're going to begin by introducing CUDA memory. At this point, you have already learned how to write a kernel in CUDA, how you can launch the kernel function in the host code, and we can generate threads, blocks, and grids. And we also know how to write if-then-else constructs and loops in a kernel. So we have a very good foundation for writing parallel code at this point. So we're now beginning to look at how we can write the parallel code in such a way that we can achieve scalability in the execution. And as we will learn very quickly, memory accesses are a major factor for scalable parallel execution in pretty much any system. So the objective is for you to learn how to efficiently use the important levels of the memory hierarchy in a parallel program. And in particular, we're going to introduce registers and shared memory in CUDA, in addition to the global memory that we have already learned. And we'll also begin to introduce how the registers and shared memory can be used to magnify the memory bandwidth for parallel execution. So this picture shows a review of the von Neumann model where we mark the two main components that we'll be focusing on in this lecture, the memory and the register file. So here we show a summary picture of the CUDA memories. So here we show the two thread blocks as a representation of thread blocks in a CUDA thread grid. So within each thread block, we also show two representative threads, thread 0 and thread 00 and thread 10. And then we also showed, for block 10, we also showed two representative threads. So in reality, we're going to have a lot more blocks, and we're also going to have a lot more threads in each block. But here is just to illustrate the important differences of the memory components in CUDA. So let's start with global memory. We have already learned global memory, and we know that the host code can use CUDA main copy to copy data into the global memory and out of the global memory. And here we also showed that all the threads in a grid can have access to the global memory. So the contents of the global memory is visible to all the threads in a grid. Now let's move up to the next level. Here we see the registers. And every thread will be able to use a set of registers to hold their private variables. And so this is shown by having the registers to only connect to their particular respective threads. So any variable that a thread places into registers will only be able to be visible to that same thread. Other threads will not be able to see the value of those variables. Now let's move up one more level here for the shared memory. All the thread blocks will be able to use shared memory. And whenever a thread block uses shared memory, all the threads in that same block will be able to see the contents of the shared memory. However, whatever a thread block, any threads in a thread block place data into the shared memory, other threads in other thread blocks will not be able to see the contents. The other thread blocks will be also reading and writing into their own shared memory, but the data in the shared memory of each thread block will not be visible to the other thread blocks. So this kind of quickly summarizes the nature of the global memory, registers, and shared memory. Here is the practical programmer's view of how we can declare variables in CUDA shared memories. So let's start with the top here. Whenever we want to use registers for a CUDA variable, we can just declare that variable as an automatic variable in a kernel function or device function. So whenever we have a variable that's just declared as a traditional C automatic variable in a kernel function, that variable becomes a register variable. And they're going to be placed into the registers, and the scope of that variable is going to be within one thread. That is, every thread in that grid will have a version of that variable, and all the versions are different. So whenever a thread changes the value of its own private copy, none of the other threads will be able to see that change. The lifetime of the variable, register variable, is going to be with a thread. So whenever the thread finishes execution, the variable also disappears. So that's why the lifetime is limited to the lifetime of the thread. Now, in the second row, we see the shared variable declaration. A variable, we can declare a variable as a shared memory variable by preceding its declaration with device and shared qualifiers. And there are two underscores before and after these qualifiers. So whenever we have underscore underscore device underscore underscore and underscore underscore shared underscore underscore in front of a variable in the kernel, then that variable is going to be in the shared memory. So the scope, as we mentioned before, a variable that is declared for a thread block will be visible to all the threads in that thread block. However, different thread blocks will have its own version of that variable. So the contents of variables in the shared memory for one thread block will not be visible to other thread blocks. And the lifetime of the shared memory is also within the lifetime of a block. That is, the block starts execution, the shared memory, variables will exist. But as soon as the thread block completes execution, the shared memory contents associated with that thread block will disappear. The third one is a global variable. We can declare a variable as global memory variable by preceding the variable as underscore underscore device underscore underscore. And this declaration will be in the host code. And you're going to ask me, how come we have not seen such a declaration? The reason is, so far, all the arrays that we use in the global memory have been dynamically allocated. This is a static declaration. So we have been essentially dynamically allocating all the arrays that we're going to transferring into the device, global memory. So that's why we have not seen this kind of declaration. So a more typical use of the global memory is actually through CUDA malloc and CUDA main copy. So, but if we declared a static variable as a global variable, then the scope of that variable will be within the thread grid. That is, all the threads will be able to see that same version. And also the lifetime is going to be in the application. That is, the application, as long as the application is running, the contents of the global memory variables will be available. But there's one important caveat to what I just said. Even though all the threads in a grid have access to that global memory, but whenever a thread changes the contents of a particular global variable, the change may not be immediately made visible to other threads and other thread blocks until the kernel, that kernel terminates. So whenever we have an algorithm that requires threads to exchange some of their computation results through global memory, we actually need to terminate the kernel before we launch another kernel where that other kernel threads will be able to see all the changes made by the threads in the previous kernel. Now, we also have a constant memory that we have not really discussed. And the reason is we're actually going to come back to the constant memory variables later on in one of the computational pattern lectures, where we're going to show in detail how you can use the constant memory. But constant memory can be declared very much in the same way as global memory variables. It's just that we use the constant qualifier instead of global, just the device qualifier. And so it's going to be in constant memory, and it's going to be visible to all the threads as well. And the lifetime of the constant memory variables is also at the application level. So just a few quick comments. Whenever we declare any variable in the shared memory or constant memory, we actually don't need to use device qualifier. The device qualifier is optional because the fact that you have a constant memory or shared memory, it already means that it's in the device. And the other kind of the detail is that whenever we use an automatic variable, it is true that this variable is going to be in the register. But the exception is if we declare an automatic variable array, then the array is actually going to be residing in the global memory, not in the register. And this will actually be, we will find in many cases, if we declare a large automatic array, the access of that array will be much, much slower than the other variables that we declare as non-array variables that we declare as automatic variables. So here is a slide that summarizes where we can make these declarations. So the rule is actually quite simple. So whenever you have a variable, you should ask yourself, can the host access the variable? If you want the host to access the variable by, let's say, doing CUDA man copy into these variables, then you will need to declare the variables outside any function. And the global variables, memory variables, and constant memory variables are in that category. So these declarations will always be outside any of the functions. Whereas, on the other hand, if the host code does not need to access those variables, in this case, the register variables and shared memory variables, then you should declare them in the kernel. So we will see that these declarations will indeed be in the kernel in our code. So now we're ready to look at a little bit more detail about the shared memory in CUDA. And shared memory in CUDA is really a special type of memory whose contents are strictly explicitly declared and used in the kernel source code. And the shared memory could be statically declared or dynamically declared. We're going to use the statically declared shared memory variables for now, and we're going to come back and look at the dynamically allocated shared memory variables in a future lecture. And so in hardware, there is a shared memory in every streaming multiprocessor or SM. And refer to one of the previous lectures if you don't remember some of the concepts about the streaming multiprocessors. And then these shared memory variables, the shared memory can be accessed at much higher speed in both latency and throughput than the global memory. In fact, the shared memory can be accessed, can provide 1 to 2 order of magnitude higher number of values to the executing threads than the global memory. So whenever we can access data from the shared memory in each SM, we will be able to access memory at more than 10 times, and sometimes close to 100 times of the throughput and the rate as we will be able to achieve with global memory. But you need to keep in mind that the shared memory is still being accessed with memory access instructions. So we still need to use explicit memory access instructions in the von Neumann model in order to access shared memory. Whereas registers are actually quote-unquote free. Whenever we need to use a register value, the register access is actually done as part of the arithmetic instruction. So we don't need to spend an extra instruction to be able to access shared memory. And this, in the case of shared memory, and this will eventually become important when we design very high performance algorithms. So shared memory, for those of you who are familiar with computer architecture concepts, is really a form of scratchpad memory in computer architecture terminology. So when we look at the hardware of a GPU for CUDA, we can easily extend the SIMD hardware picture with shared memory. So recall that in a CUDA GPU, we have these processing units that are executing in SIMD mode. So we're showing multiple processing units controlled by the same control unit here. So the shared memory is actually in the processor, in this case the SM, and then the shared memory is accessible by all the processing units in the SM. So those are the arrows that I show on the side here. And then the shared memory is able to provide many operands per clock cycle, more operands per clock cycle than the global memory can. So in this picture, the global memory corresponds to the original von Neumann memory, and the registers are still in the register file. But here we added a shared memory in the processor close to the processing unit with a lot more bandwidth for providing the values into these execution units. However, even though the shared memory is much faster and better, but it actually, because it needs to fit into the processor, it's quite small. So we will need to be able to, to use a much smaller memory in order to have much higher bandwidth of access. So now this brings us into to how people typically use something like a shared memory in CUDA. And the common programming strategy for using shared memory is by partitioning data into subsets or tiles that fit into shared memory. In some languages and literature, these tiles are also referred to as blocks. However, because the CUDA terminology has thread blocks, in order to avoid confusion, we're going to call these subsets tiles rather than blocks. And so every time we execute a piece of parallel code, we actually try to use each thread block to focus on a subset of the data or a tile of the data at each point in time. So we would have all the threads in the thread block to cooperate and load the tile from global memory into the shared memory. And because we're using multiple threads to load the data, we can do this with good amount of parallelism. And this is called memory level parallelism in literature. And then once we have the tile in the shared memory, we will perform the computation on the subset from in and out of shared memory rather than global memory. And this allows us to do the computation much faster because the shared memory can provide these values to the processing unit at much higher speed. And then once we finish the execution processing of the data in the shared memory, then we actually write the results from the shared memory into the global memory, and then we go and iterate and go to the next subset or the next tile. So we go through this process in an iterative manner until we finish the entire data set. So this is called a tiled algorithm strategy, and we're going to see more details in the next lecture. Now, here is a simple example of how you can declare shared memory variables in a CUDA kernel. So here we show the matrix multiplication kernel, and we show that we're going to have two variables, two array variables, A and B. So these two arrays are going to be of tile width on each side. So this is tile width by tile width. So this is the size of one of the tiles in the input A and input B matrix. So we're defining a small array, a tile size by tile size small array for A, and then a small array for B. So in every, as we will see, at every stage of the computation, we're going to bring one of the tiles of A and one of the tiles of B into the shared memory arrays. And here we just show the declaration, and you see that we precede the declaration of this array with shared qualifier. And also, because we have a static declaration of the shared variables, we can actually use the two-dimensional array notation in C, and we don't need to linearize the index when we access statically declared shared variables arrays. However, if we choose to do dynamic allocation, then we will need to linearize the access. So this is we're going to come back to this point later. So now you have a good basic understanding of the three levels of the memory hierarchy in CUDA. You have seen registers, you have seen shared memory, and of course you have seen global memory. So in order to, if you'd like to learn more about the concepts and the usage of these different variables in different levels of the memory hierarchy, I'd like to encourage you to read the sections 5.1 and 5.2 of the textbook. Thank you.